is number 18, I believe, in your sapling assignment. Again, just reading through what appears on mine, yours might be just a little bit different, but it'll be the same idea. A certain substance has a heat of vaporization, and that's given to us as 27.33 kilojoules per mole, kJ per mole. At what Kelvin temperature will the vapor pressure, and I know we're going to need two temperatures, and we're going to end up having two pressures, and just because we're going to be using the Clausius Clapeyron equation. So what we're looking at is the following information. At what Kelvin temperature will the vapor pressure be 6.5 times higher than it was at 299 Kelvin? 299 Kelvin. So looking for a new temperature when, let's just suppose I had 1 atmosphere or whatever the pressure unit wanted to be, and now at the second pressure it's 6.5 times larger. So just using any numbers really that are 6.5 to 1 in proportion would solve this equation correctly. We have all of the information provided to us except for the second temperature. We know that our Clausius-Clapeyron equation compares the natural log, and just kind of remembering how it's graphed, the natural log on a y-axis compared to the reciprocal of the Kelvin temperature produces this negative slope where the slope of the line is represented as negative delta H of vaporization over the gas constant R, where R from our good old-fashioned Pv-Nert days is 8.31 joules per mole Kelvin. And that's provided for us right here in the hint. I had to pull up that hint for us right there. So it's a graphical representation of how pressure and the Kelvin temperature relate to the heat of vaporization. Given any 2 points, the slope of the line, notice that the slope is negative. That's why we have the negative here, because this value is always positive. So it's really just turning into a plug and chug type of formula. So let's take that one step at a time. We have the natural log of the ratio of P2 over P1, and that's coming up here. There's no units, but that's okay. As long as they're the same units, this ratio works just fine. 6.5 compared to 1 is showing a pressure that is 6.5 times larger than the original. Alrighty. The delta H of vaporization was given to us as 27.33. Notice that's in a kJ per mole. But I also want to make sure that I have an agreement here with the R constant, and the R constant is clearly given in a joule per mole Kelvin. So I'm going to actually remember that I have to multiply this number by 1,000 to represent that heat of vaporization, so that when I set it over 8.31, the gas constant, joule per mole Kelvin, I have like units. Alrighty, and then we need a little more page. We have the multiplication times the reciprocal of both temperatures. So T1 was given to us as 299 Kelvin. And we're going to subtract that from our T2, the ultimate variable that we're trying to solve for. And I just ran out of room here on the edge. So remember that this is all one side of the equation. Alrighty. So let's kind of give ourselves some room here. We're going to start the algebra process of solving this equation. So we have the natural log of 6.5 over 1. Let's hit that. I'm going to literally hit ln on your key sequence. You see that button? Not LOG, but we want the LN button, and you're going to literally hit 6.5. So natural, oops, I got to turn it on. Natural log, and a parenthesis comes up, 6.5, close your parenthesis, equal. And I'm getting a value of 1.871802177, so I've just simplified this portion. I'm going to set that equal to, next thing I'll do is just simplify this expression. So I'm going to start by saying 27.33 times 1,000 to get that into a joule, and I'll divide that by 8.31. And my screen says 3288.80866, so I'll just round that a little bit. And I still have the expression for the temperatures, 1 over 299 Kelvin minus 1 over T2, the ultimate variable we're targeting. So in the next step, to simplify this, I'm going to divide both sides by 3288.81. Whoops, wrong decimal place. So that's 3288.81. So let's do that. I have 1.8718 divided by that previous answer of 3288.81. And now I'm getting a value of a real small number, 5.6914. Look at the very end of your screen, times 10 to the negative fourth. And that's equal to 1 over 299 Kelvin minus 1 over T2. Now, this expression in the next step of algebra, this expression, the reciprocal of 299, I'm going to bring it over here to the left side, I'm actually going to subtract from both sides. Remember, this is just this number minus this number. Since this is positive, I have to subtract it from both sides. So what I'm doing is getting an expression where 1 over T2, with that minus sign still in front of it, is going to remain on the right-hand side. So on my screen, I have 5.6914 e negative 4, and I'm going to go minus parenthesis 1 divided by 299, close parenthesis, equal. And I get a value of negative 0.0027753 and so forth. That's equal to the reciprocal of T2. So how do we pull out T2? Well, really the T2 and that value just switch sides. So I'm going to divide both sides by negative 1. And now I just simply have positive values. Alrighty, so the negatives just simply canceled one another out. And the algebra here now, T2, can be found by taking 1 over 0.002775. It's like multiplying both sides by T2. Alrighty, so T2 is 1 divided by 0.00725. Just these guys end up switching places. 1 divided by previous answer on my calculator screen, and the Kelvin temperature is 360.32 Kelvin units. Let's consider sig figs. We had 2 decimals here, 2 decimals, no decimals on that temperature. So we'd probably have to put 360.32 to keep the decimal numbers, or it may ask you for the Kelvin unit. Right? So just to practice with the equation where we were given all of the information except one target, and we solved the algebra to pull that out. And I hope you found this video helpful.